paper that was meant to provoke a discussion, live discussion at the conference. So I'm afraid that it will not work as intended in this online form, but well, let's try. So I will start with some context and inspiration. So the theme of this work is shaping the future of the field, and the call for paper had this statement that the organizers invite short papers which explicitly address the themes and the future of the field. And another part of the context is that last year at Ryan Baker had a keynote where he outlined 6 challenges which were inspired by famous Hilbert problems in mathematics, 100-year-old problems, with difficult problems with clear and specific goals. So I was inspired by this Ryan Baker's list of challenges. On one hand, I agree with many of the high-level goals that he outlined. On the other hand, I do not completely agree with the aim of trying to have these challenges with clear specification of goals. I think, and that's the argument that I try to make in this paper, that we should focus that our discipline is inherently has many ill-defined problems which are hard to grasp, and we should embrace this nature of our domain and shape the research accordingly. So that's the basic context. I think that concerning this high-level point, an interesting comparison is with net fixed price, which is something that happened in a closely related area, recommender systems which share with our area a lot of commonalities. I guess many of you know the net fixed price. I just recapitulate, it was a price for $1 million by the company Netflix some 10 or more years ago. And it was a typical challenge with clear goal. The goal was to improve some root mean square error of predictions by 10%. It was a difficult challenge. It took some 2 or 3 years to achieve the goal. And this challenge was definitely an interesting impulse for research. It drew a lot of attention to the field of recommender systems, partly due to the $1 million price, of course, but also due to the fact that it was clearly defined task, clearly defined difficult goal. So definitely that's a positive impact by focusing the research and improving the research. On the other hand, this prize had a quite limited practical impact. The techniques that were developed within the contest were not the techniques that really moved the field forward that were used in the practical implementations. Like for the practical implementation, other aspects like diversity of recommendations or taking contextual information into account turn out to be more important than the things that were in the challenge. So I think this is something that's it's a bit different area than ours, but it's something that is good to have in mind. So in this short paper, what I discuss are 3 areas of challenges that I think are interesting, important, and where we do not have a clear goals, but we should focus our research in these directions. I want to make clear that I do not claim these are the most important challenges. It's just something that I base on my experience, which is specific. I work on development of learning systems for kids and on analyzing the data from such systems. So it is definitely based on my experience, something that I think that are interesting research challenges. And I would be glad to hear your opinions, where you see challenges at the end of the talk. So I will discuss these trade-offs, methodology challenges, and scalability issues. So trade-offs. Trade-offs are something that's prevalent in our area. In many cases, it's not like that we need to optimize one clear criterion. We often have to make trade-offs between different goals. So, for example, from my practice, one typical trade-off is in master learning, setting master learning thresholds. If we set them too high, it will lead to unnecessary over-practice and the learning will not be efficient. If it's too low, it will lead to under-practice and the students will not learn as much as they should. Another typical trade-off is engagement learning. Sometimes if we make the practice engaging, more fun, it will be at the cost of learning. On the other hand, if we focus on learning, it may not be totally engaging. So often we need to balance these two. Hints in learning systems typically lead to some trade-offs. Like if we include hints in systems, it can support learning of students, but at the same time, it brings a risk of gaming because some of the students can abuse the hints to just go through the system. Dashboards should be focused on comparison with others. It is motivating for some students, so it can improve the motivation and engagement. On the other hand, comparison with others can be demotivating or frustrating for weaker students. So again, there's a trade-off in the focus on comparisons. Interests of students and interests of researchers can somehow go against one another. So researchers want to explore new techniques. For example, they need sufficient data to make statistically robust conclusions, but this can be at the cost of inferior practice for some of the students. Or in student models, there may be a trade-off between model accuracy, how precise the model predictions are, versus implementation simplicity, which is also practically important for applications. So these are just some examples of the trade-offs that we face. These trade-offs are typically hard to study, and that's maybe one of the reasons why they are not that much studied in research studies, because if you want to optimize prediction accuracy, that's something that you can easily measure and you can easily optimize it, compare models. But if you want to choose a good threshold measure for master learning or a suitable degree of comparison in dashboards, it's very hard to evaluate and hard to measure. But at the same time, it's practically very important. So we should really, I think that one of the research areas that we should focus is to study techniques for evaluation of these trade-offs. For example, methods for visualizing trade-offs. Here I have an example of one of my studies where we have studied this master learning criteria, and where we try to study the trade-off between effort, how long students spend in practice, and score, how well they know the stuff when they finish the practice. And we have visualized these curves for different master learning thresholds. So I think this was a very simple method. I think we need more of these visualizations for trade-offs. Then exploration using historical data. If we are, for example, optimizing some predictions, we can typically evaluate this using historical data. If we want to evaluate the impact of some of these thresholds, it's typically very hard to do using historical data. It's best done using live experiments, A/B testing with new students, but that's expensive. So it would be definitely useful to have at least some insight using the historical data, which is, however, quite difficult. And also it would be useful to study optimization with respect to multiple criteria, which is very relevant to these trade-offs. Then methodology. A lot of typical current research, and this is also true kind of for the Baker's challenges, works in the following way: that we have some data, we do analysis of the data and report results for specific performance metric like area under curve, which is used in some of the Baker's challenges and so on. And often in a research paper, little attention is paid to methodological details. Also in the Baker's challenges, there's not much attention into details how the area under curve should be computed for the experiments and so on. And there's only some comparison with a constant. And this can be quite problematic. I think that by now, kind of famous case study in these problems is the deep knowledge chasing paper, which was like the first paper which tried to apply deep learning techniques for student modeling. And the paper reported large improvements with respect to area under curve compared to state of the art. And so it argued that deep learning brings a lot of advantages. But subsequent research, and there has been several research studies that examine these results, show that most of the improvement was due to some specific problems in the evaluation methodology and not due to some inherent properties of deep learning techniques, neural networks for this domain. So in methodology, details matter. And for me, this is like an area where I have spent a lot of my research effort. Recently, I have written an overview article about these methodological nuances. So some of these details that are important are the presence of biases in data, like the master attrition bias or ordering bias, where students traverse the problems in the same order. These biases can influence non-trivially the results of comparison. Or the choice of metric, like whether we use area under curve, root mean square error, mean absolute error, or some other metric. The choice of the metric is often not discussed much in research papers, but it's going to have non-trivial influence on the evaluation. Some of the metrics, like mean absolute error, in the case of probabilistic evaluations, can be shown to be clearly wrong, but they are still sometimes used. Other metrics, like area under curve, I believe, are kind of overused. used uncritically, even in situations when they are not completely appropriate. So this, there should be attention. Also, details of metric computation, like for example, averaging. Do we compute to measure globally overall data, or do we compute the measure for each student and then we compute an average? These different methods of computation can again influence the results, and they are often not even documented well in papers. Another methodological detail is division of training and testing set in cross-validation. You can use different kinds of stratification, like student stratified data, item stratified, and so on. And again, this can influence the results of comparison. And I think that this thing needs more attention, and they offer interesting challenges and research opportunities. For example, I think the important step is just to clarify these methodological issues, clarify which of these data do matter, and develop a clear naming terminology so that we can talk about them, so that we can document our methodological choices in papers. For this, I believe a useful tool are simulated data. So for example, in psychometric research, the use of simulated data has long tradition. People are using it a lot. In learning analytics and education data mining, you can sometimes meet simulated data, but not that much as in psychometric research. And I think that it would be useful. Of course, the basic thing for research are real data for real students, but simulated data can complement them quite nicely. And particularly for dealing with these methodological challenges, I think they are very useful. And for example, the dealing with biases, how to detect biases in data, how to clarify the impact of biases on data, how to avoid biases, these are all interesting research questions. Another direction for research, interesting challenge is clarifying what works when. Often we have several techniques which are shown in different papers to work, and the results are often conflicting. And typically this is because each of the papers has used different contexts, different domain, for example, mathematics versus programming versus language learning, or different population and so on. So I think it's very useful now to try to clarify which techniques were under what circumstances, for example, by mapping different techniques to a knowledge learning instruction framework, which is a good framework for this kind of clarification. And I generally believe we need more systematic application and production of previous studies, but for this clarification of what works when, but also for checking of the methodological details, how they influence the results that were already published. And finally, the third topic that I want to highlight is scalability. And here I mean both computational scalability, which means that the techniques that we develop should work not only on small academic examples, but on real-life traffic and real-life data, which are often orders of magnitude larger than the ones presented in research papers. But I also mean development scalability, developing systems under real-life constraints. For this, I would like to describe briefly my perspective, my experience, which may clarify my point of view. I work on adaptive practice systems in context of Czech Republic for Czech students. We are doing practice for many domains: mathematics, Czech language for native speakers, English for second language speakers, programming, geography, and so on. We work with a rather small team, like 2 computer scientists, I and my former PhD student who is the main developer of the systems, and then we have a small team of content creators who work just a few hours a week on creating the questions and problems. Even in this small team, we are able to achieve a system which has something like 10,000 students daily. Actually, during the last 14 days when schools are closed, we have much larger traffic even, and we are starting to see commercialization reasonable. I think my perspective is slightly different from the core of the people in the domain. Here I have a slide from the introduction to this conference, where was the visualization of different countries of origin for authors. And here we can see that the center of this community is in big English-speaking countries: United States, United Kingdom, Australia, Canada. And I think that people from these countries have slightly different perspective than I, for example, and many others. If you develop systems for English-speaking learners from these big, rich countries, then it makes sense, for example, to develop a tutoring system for fractions and optimize the hints within such a system. Because in English-speaking countries, there are many products for learning, and you can can get the funding to develop, to have a quite large team to develop a specialized product. Maybe the people in the countries do not have the impression that it's easy to get funding, but compared to the rest of the world, it's really different. So, and I think that many people in the world live and learn in countries where even simple practice systems which cover a lot of the mathematics, for example, are very useful, which is a kind of different perspective. So with this perspective, like our setting and setting of many other people in small countries, I think it's really important to focus on development scalability, on being able to develop large-scale systems within a reasonable small team. And for this, it's very useful to have research-based techniques which will allow us to develop these systems efficiently. To have techniques, for example, for developing and managing content. So in our systems, we have like tens of thousands of items. So even if you are developing a system for some like small language, like Czech or some even smaller language, you still need the tens of thousands of items that you need for English. Even if the target audience is small, the language is still, the complexity of the language is the same or even higher than English. And so for developing and managing the content of this size, it's very useful to have analytics techniques. In student modeling, when we take into account this development scalability, we want to focus not just on predictive accuracy, but also on model simplicity and the number of parameters of models so that the models are easily applied. So for example, I tend to use and to advertise L rating systems, which is a system originally from chess. It's kind of, and it can be quite easily used for modeling students. And it has the advantage that it has few parameters and it is very easy to implement. It can be implemented easily by basically any undergraduate student in computer science, as opposed to Bayesian noise tracing or additive factors models or some more complex models of this type, which are quite tricky and not easily implementable. And also, I think it's very useful to have sometimes a debugging perspective to just take into account that people make mistakes, that we as a developer of systems make mistakes, and we could use techniques which try to find us the most important mistakes in our systems. I think here we can take inspiration from software engineering, where in software engineering there are whole conferences devoted to finding bugs because they acknowledge that programmers make bugs, and so we need techniques for finding the bugs in the system. So similarly, I think it's very useful to, a lot of research in our areas is focused on finding and providing feedback to students, but maybe we should focus also more on providing feedback and finding bugs in our stuff, in our content, in our systems. So here, many of these scalability issues are quite practical, but at the same time, I think they can offer interesting research problems. So for example, for me, this focus on developing and managing large-scale content led to interesting research on item similarity measures. How do we measure similarity of two items? Because this is very useful for managing these tens of thousands of items. Also, I think developing models which are at the same time simple, robust, and at the same time provide a reasonable predictive accuracy is an interesting research direction. The finding of bugs can be done using different outlier detection techniques, and there are some of the research opportunities. Some of these issues with developing and managing content are related to the research which has already been published concerning Q-matrix validation requirement, techniques for domain modeling and checking our domain models based on the data that we have. To conclude, I would like to go back to Ryan Baker's challenging and discuss some of our agreements and disagreements. So this is the list of Ryan Baker's challenging. He focuses on high-level things like transferability, generalizability, interpretability. His goal was to formulate these goals in such a way that we have a clear, measurable goals. So the common points I think that I share with Ryan is that the research for practical impact, both his challenges and my take on challenges, is to a large degree motivated by that we want to have a practical impact. And I think that on high level goals, like what we should aim as a community to achieve, we are kind of in agreement. The difference is that Ryan tried to formulate his goal in such a way that it would be clear and measurable whether the goals were achieved or not. Whereas I try to argue that we should acknowledge that in our community the goals are not clear, and also I try to argue that we should focus a lot on the methodology, on like research and techniques that we use for evaluate our research, kind of meta research, if you will. A small note about competitions, like these challenges, if clearly defined goal, I see as a good way of competing within different research group. I think this can be very good for quick progress in specific direction. For example, I tend to use a lot of these competitions with my students because it gives them a clear focus and we can move quickly in some direction. But I believe that for like guiding long-term programs, long-term priorities of the community, they are less suitable. So that's all of me. As I said, this was my take on the challenges, like based on my personal experience, some of the challenges that I see. I welcome your questions, but maybe even more than questions, I welcome your take on this issue, maybe your observations about what you see as the challenges for our community. So thank you for your attention.